Okay.
Okay, I think we can now start. So, hello everyone. I know that everyone is joining from different parts of the world. So, good morning, good afternoon, good evening. My name is McDonald Chirara. Welcome to our second lecture at Connecting the Young World Fair. So, today we have a very special guest. We have Dr. Will Kinney. So, Dr. Will Kinney is a professor in the Department of Physics at the University at Buffalo, SUNY, where he has been on faculty since 2003. Dr. Kinney received his Bachelor of Arts from Princeton University and PhD from the University of Colorado Boulder. He has worked as a research associate at Fermi National Accelerator Laboratory, the University of Florida, and Columbia University, and also held visiting positions at Yale University, Perimeter Institute of Theoretical Physics, Harish Chandra Research Institute, the University of Chicago, the University of Valencia, and Stockholm University. Dr. Kinney's research focuses on the physics of the very early universe, including inflationary cosmology, the cosmic microwave background, dark matter, and dark energy. He has authored more than 70 published research articles and received the SUNY Chancellor's Award for Excellence in Teaching in 2014. Thank you very much, Dr. Will Kinney, for joining us today. So I'll now leave the podium to you.
Thanks very much. It's a real pleasure to be here. Thank you so much for inviting me to talk. I'll get right to it. So what I'm going to talk about today, let me reshare my screen here real quick. That should do it. You guys can see the screen okay? Yeah, good. Okay. So I'm going to talk today. I'm going to start and just tell you, spend 20 minutes or so talking about giving you sort of a summary, a very high level summary of, the kind of problems that I work on, and a little bit about things like how the basics of cosmology work and cosmological expansion and so on. And at the end of my talk, I want to spend a few minutes just giving a little bit of a sort of, I know that one of the ideas here is that this is supposed to be giving advice to those of you who are here who are interested in careers in STEM and so on. And I thought I'd just give a little bit of my own perspective on that as well at the end of the talk. But let's start by talking about physics, because that's what I do. And I know that not all of you are physics students. Am I correct about that? Yeah. Some of this I think you'll find fairly easy to follow. Maybe a little bit will go a little bit over your head. Don't worry about it too much. But I'm going to try to keep it at a level that's understandable even for people who aren't physics students in particular. So I do cosmology, which is the study of the universe as a whole. So it's and in particular, it's the study of the structure and the history of the universe, which are in fact really intimately related to one another, right? So that the overall structure of the universe today is pretty much determined by gravity. And gravity is, for example, in Einstein's theory of general relativity, gravity is geometry. They're really the same thing. And so any story that you tell about the history of the universe is also a story about its structure. And one of the neat things about cosmology, unlike, for example, archaeology, where another science where you study the past, is that in cosmology, we study the past all the way back to the very beginning of the universe. And I'm going to talk about that in a minute. But unlike say, an archaeologist who has to dig up fossils and reconstruct the past from indirect evidence. We can actually just go out and look and see the history of the universe as it unfolds. The reason for this is because the speed of light is finite. And in particular, when we look out in space with a telescope, we also look back in time. Telescopes are time machines. So for example, when we look from the Earth, when we look at the sun, because it takes light 8 minutes to travel from the sun to the Earth, we're seeing the sun not as it is right this second, we're seeing it as it was 8 minutes ago. Similarly, when we look out from where we are out on the edge of the Milky Way galaxy, if we look to the center of the galaxy in the constellation of Sagittarius, where there's a 4 million solar mass black hole lurking in that central region of our galaxy, we're actually looking out a distance of about 30,000 light years. So that means that we're looking back in time about 30,000 years. We see the center of our galaxy as it was 30,000 years ago. Even more so when we look further out in the universe, if we look, for example, at the light coming from a distant galaxy, that galaxy might be 100 million, 500 million, a billion light years away. So we're seeing that galaxy as it was 100 million years ago, or 500 million years ago, or a billion years ago. So the really beautiful thing about cosmology is that we don't have to speculate on what the universe was like a billion years ago. We can just go out and look at it. And if we look out, I have a telescope that can look out 1 billion light years, we can see exactly what the universe looked like a billion years ago. So the idea of a telescope as a time machine is the central concept that makes cosmology possible. And in fact, so we know that the universe is about 13.8 billion years old. This is actually really precisely measured now. We know the age of the universe to within an uncertainty of about 200 million years. So 13.8 billion plus or minus 200 million years ago, the universe started, and I'll talk about the Big Bang in a minute. But that means that if we built a telescope that was capable of looking out 13.8 billion light years, we could actually see the Big Bang itself. And in fact, we have done that. That was first done in 1965. And I will show you an image of what such a telescope, an image from such a telescope looks like. So I'm going to start by showing you this picture, which is called the Hubble Ultra Deep Field, which was taken by pointing the Hubble Space Telescope at a point in the sky where there are very few foreground stars from our own galaxy, the Milky Way. You can see a couple of them in this picture, this one here and this one here, these things that are have these little spikes on the side. Those are foreground stars, but almost everything else in this picture is extragalactic. It is things that are out there in the universe. So this picture was taken by pointing the HST at a blank spot in the sky, opening the shutter and leaving it open for an exposure of about 11 days. And you are seeing, as you look out, what you see here in this picture is almost all galaxies, groups of 100, 200 billion stars or so. The universe on the largest scales, the basic building blocks of the cosmos, are galaxies like our Milky Way. And as you look further and further out into the dimmer and dimmer galaxies in this picture, you're seeing the universe as it was when it was younger and younger and younger. So the very dimmest stars, the very dimmest objects you see in this picture, the most distant ones, are galaxies that were just in the process of forming when the universe was only about 10% of its current age, about 1 billion years old. So in this one picture, we see the entire history of the universe from about 1 billion years after the Big Bang today, stretched out into a single image that is taken, that is the Hubble Ultra Deep Field. So this is a beautiful picture that shows a large fraction of cosmic history all in one image. One of the things that we learn immediately when we look at external galaxies is we discover that they're all moving apart from each other. The universe is expanding. So all of these galaxies in this picture are moving away from all of the other galaxies in the picture. And they're also all moving away from us, and in such a way that the further away they are, the faster they're moving away from us. Now that might make you think, wait a minute, that means we're at the center of the universe, right? Or another way to put it is, I know that even among physicists, there's a lot of misconceptions about how the Big Bang really works. People tend to think of it as everything's concentrated into one little spot and there's an explosion and everything flies out in all directions from that explosion. That is completely wrong. And that is the first thing the first misconception that I want to try to undo. Here's a better way to think of the physics of the Big Bang itself and the expansion of the universe. Imagine, and this is a two-dimensional analogy, but generalizing it to 3 dimensions is not hard. So imagine you take a flexible, like a rubber sheet, something that a stretchable sheet of rubber or something like that, and draw an even grid of squares on it, right? So that every square is exactly the same size. Now, in fact, you could imagine, it doesn't take much more imagination to imagine this stretchable sheet extending off infinitely in every direction. But of course, we can't draw that. We can only draw a finite piece of it, right? So take this infinitely large stretchable sheet and draw a completely even grid of squares on it. It's easy to see that no spot on this sheet is any different from any other spot. All the squares are exactly identical, right? So now make every square bigger, such that the squares are still all identical. The grid goes off infinitely in every direction, but now every square is a little bigger, and every point on this grid is a little further away from every other point than it was before. There's no center to this, right? Every square is exactly the same, but now we can make the squares bigger and so on. And this is a much better analogy for cosmological expansion. The space, note that this grid isn't expanding into anything. All the squares are getting bigger, but it's all the expansion is happening within the space itself. And it's easy to generalize this to 3 dimensions. Just imagine a grid of cubes and all the cubes are getting bigger, right? And so this is an analogy for a geometrically flat universe, which data indicate is the kind we live in. And the important properties of this are that the universe has no center, there is no preferred place in the universe, and there's no edge. And in fact, in this case, no edge means that the universe has to be infinite in extent. But also notice that as the universe expands, everything is moving away from everything else. So everyone sees themselves at rest, for example, on, one of these points on the grid, and all the other points on the grid are moving away from them. So everybody sees themselves sitting still and the rest of the universe moving away from them. So every observer in this completely uniform universe sees themselves at the center of the expansion. Now, what about the Big Bang, right? So now turn time backwards. If we run the movie backwards, what happens is if we go back in time, or if we take a telescope and look further out into the universe and further back in time, what we see is that this grid got smaller and smaller and smaller. So as we go back in time, everything got closer and closer together, but the universe as a whole, this grid is still infinite. So the universe becomes more dense, but it doesn't become any smaller. And in fact, if you plug this into Einstein's theory of gravity, what you find is at finite time in the past, this grid of squares goes to 0 size. This is called the initial singularity. It's called the Big Bang. So the important thing to recognize here, and we'll see another way of looking at this in a minute, is that the Big Bang didn't happen at one point in space. It actually happened everywhere in an infinite space at once. Even a tiny fraction of a second after the Big Bang, the universe was completely uniform and infinite in extent. The Big Bang happens everywhere in an infinitely large space at once. And then the universe proceeds to expand outward in this completely uniform and even way. So there is no location of the Big Bang. It happens everywhere in space at once. This is the idea of uniform cosmological expansion and a Big Bang. Now, the universe is infinite in this model. It may, in fact, in reality, of course, it may close off on itself in certain ways, but we'll leave that for a moment. But the thing is that even in this infinitely large space, we're only allowed to see a little bit of it. That's because the universe has finite age and light has a finite speed. Right. Remember, when we're looking out in space, we're looking back in time. So imagine an observer sitting here at some point in the universe, some point in space. If the universe is only 1,000 years old, that observer will only be able to see out 1,000 light years, because any further than that, and the light hasn't had time to get to them yet. So the distance that we can see out in the universe is equal to, roughly speaking, the speed of light times the age of the universe. When the universe is 1 year old, you can only see about a light year out. When the universe is 1,000,000 years old, you can only see about 1,000,000 light years out. There's another factor that comes from expansion, but this is the basic principle. So as the universe gets older, 2 things happen. One is that the squares get bigger. And the second is this distance that the size of our observable universe, the distance we can see out, expands outward at the speed of light. So as the universe expands, we see more and more and more of this infinite universe, but at any given point, we only see a finite bit. This is called our horizon. It's the size of our observable universe. So early on, this observer that is maybe us, and somebody else in a distant galaxy, they would be outside of our observable universe. They'd be moving away from us faster than the speed of light, which is okay in these kind of models. And as the universe gets older and older and older, we see more and more of it, and eventually it will get to a point where we can see this other observer, and they fall into our horizon. This is, these horizons in cosmology are not all that different from horizons on the Earth, right? Think about on the spherical surface of a planet, we can only see out a certain distance because of the curvature of the planet. Somebody else standing somewhere else is going to have a different horizon. But everybody sees pretty much the same thing, that they can only see a finite little piece of the spherical surface. Likewise, in cosmology, every observer has their own horizon size. Everybody has their own observable universe. Now, what does this look like from our point of view? In fact, remember, looking out in space is looking back in time. So this is a nice diagram of sort of a cutaway of our entire observable universe in one picture. Is that if we look out, for example, with Hubble Space Telescope, the further out we look, the further back in time we see. So the Hubble Ultra Deep Field, for example, goes out to when the universe was between 400 million and 700 million years old. And the current age is about 13.8 billion. The further out in space we look, the further back in time we go. And in fact, if we go out all the way to 13.8 billion years, we would see the Big Bang. And moreover, we would see it. Remember, the Big Bang happens everywhere in space at once. But looking out in space and looking back in time, that means no matter what direction we look, if we look out 13.8 billion light years, we would see the Big Bang. So the Big Bang is not a point in space that's somewhere out there. The Big Bang is a sphere with us at the center of it. So if we look out in space and back in time to this other point in space, what we see anywhere along the spherical horizon of our observable universe is the Big Bang itself, and there's absolutely nothing beyond it. So the universe itself at any given time is infinite in extent, but because the light takes finite time to travel to us, where we would see the Big Bang is everywhere in a sphere with us at the center. And every observer would see the same thing. This observer would see the Big Bang in a sphere there. We see the Big Bang in a sphere there. So in fact, the Big Bang is not astrophysically something that happens at a point in space that we can go out and look at. It happens in a sphere with us at the center. And the edge of that sphere is the edge of our observable universe. In fact, we can't see all the way out to that edge of our observable universe, to the sphere of the Big Bang, because very early on, the universe was very hot and dense. You know, if you go back in time and you crunch everything together, that means everything's going to get denser and it's going to get hotter. And so the very early universe was extremely high temperature, extremely high density, which means that light couldn't travel very far. Light bounced around and had a very short path. So the universe was cloudy. It would be like being in a fog in the very early universe. You couldn't see very far. That fog cleared in an event called recombination that happened when the universe was about 380,000 years old. And the physical process that happens here is very early in the universe when the temperature was above about 3,000 Kelvin. That was hot enough that all the electrons were stripped off the atoms in the gas in the universe. And in fact, the gas in the universe was very simple at the time. It consisted entirely of hydrogen and helium in a ratio of about 4:1 by mass. And all these hydrogen and helium nuclei were ionized. The electrons were stripped off, and the light would bounce off these charge-free electrons very rapidly, and the universe would have been just an opaque cloud, glowing at about the temperature of the sun. As the universe expanded and cooled, eventually the temperature of the universe dropped to a point where these electrons got captured by the hydrogen and helium. The atoms became neutral, and that meant that the universe suddenly became transparent, and the light that was bouncing around in the early universe could now just stream freely through space. So there is this leftover light from the Big Bang that streams in all directions and is released when the universe first became transparent, which happened about 380,000 years after the Big Bang. Now, remember, looking out in space and looking back in time, what we see then is if we try to look out past that point, the universe was an opaque cloud and we can't see anything. So we can only see out to this sort of spherical thing called the surface of last scattering, which is this light coming to us, this leftover light from when the universe was 380,000 years old, is coming toward us from all directions in the sky. This is called the cosmic microwave background. It's the relic light left over from the Big Bang. And this is what I mean when we say we've built telescopes that are capable of seeing all the way back to the Big Bang, is here's a picture of it. This is the sphere of the sky. So we're at the center of this sphere. And this is actually light that was emitted when the universe was 380,000 years old and has been traveling to us unimpeded ever since. And this is a picture of the primordial universe. This is what the baby universe looked like when it was only 380,000 years old. And that baby universe was almost completely uniform. These are the little non-uniformities or perturbations in the gas in the early universe, spots that were a little hotter and a little cooler than their surroundings. But it was uniform to one part in about 10 to the fifth. So the temperature of it was a completely uniform gas, temperature of about 3,000 Kelvin, with little hot spots and cold spots that changed at about 1 part in 100,000. And it was made up entirely of hydrogen and helium. And while there's also some dark matter in there, and we'll mention that briefly in a second. But the early universe was really simple. And more to the point, we can actually see it. This is an actual image of real light coming to us from when the universe was at its youngest point. And this is as far out as is possible for us to see using optical telescopes. This is as best we can do with light. And this is a picture of the infant universe. So what I want you to take away from this is that we can actually observe the history of the universe with telescopes all the way from when it was about 300,000, a little less than 400,000 years old, up to the present day at 13.8 billion years. And we can observe the entire history of the universe playing out like a movie in our telescopes as we look further and further out in space and further back in time. And what do we learn when we put all this together? We have to explain how this history works. And what we find is, and I'm not going to belabor this point a lot because I want to go back to the physics of the Big Bang, which is what I study mostly, is that the universe is only composed of about 4% of stuff that we know what it is, right? So all the atoms, everything on the periodic table, the hydrogen, the helium, the carbon, the iron, all of that stuff only comprises about 4% of the total stuff in the universe, the total mass density of the universe. This was kind of a surprise, as you might imagine. 23% of the mass of the universe is in something called cold dark matter, which clumps and forms structure under gravity the same way that atoms do, but it doesn't appear to interact with light in any way. We have no idea what this stuff is. All we know is that it doesn't interact with light, but it collapses and forms structure under gravity. And we can see it because of its indirect gravitational effects on the atoms that we can see. 73% of the universe is in something even weirder called dark energy, which also, like dark matter, does not interact with light. But the thing with dark energy is it also doesn't clump under gravity. It stays completely smooth. And furthermore, instead of slowing the expansion of the universe down, like you might expect, gravity pulling everything together, you would think that the expansion of the universe would gradually be slowing down. Dark energy has a weird opposite effect where it actually pushes the expansion of the universe faster and faster. It makes the expansion accelerate. Well, at this point, I'm fond of quoting King Alphonse of Castile, who was a Spanish king who reigned from 1252 to 1284. And he was a great patron of the sciences. In particular, funded the creation of what are called the Alphonsine tables, which were the best astronomical tables of the time. And he was a student of cosmology, and his opinion on the Ptolemaic system, the geocentric system that was the cosmological model at the time, he said, if the Lord Almighty had consulted me before embarking on creation thus, I should have recommended something simpler. Okay. I'm trying to decide how much more I want to do on the physics end. How much time left should I have? So I've been going for about 20 minutes. Is that about right? Let me spend a few minutes running through this. This is a little bit more advanced. If it goes over your head, don't be too concerned about it. If one of the organizers wants to give me a time check in the chat box, that would be helpful. So another way to think of the universe, like I said, this is more aimed at some of the physics students in the audience, is to draw a diagram not just of space, but of space and time. So we can put spatial directions on, for example, on the horizontal axis and time on the vertical axis in such a way that if we measure things in the right units, we find that anything traveling at the speed of light, so a moving object is going to go outward in space as it goes upward in time. And anything traveling at the speed of light will then execute a 45-degree line on this diagram of space and time. So every object has a path through space-time called a world line, and anything moving slower than the speed of light will stay inside this 45-degree line. So if I start at some point in space and time, for example, here and now, anywhere that I can go, if I travel less than the speed of light, is inside this region that is defined by this 45-degree line of light rays. It's called the light cone. In order to go outside this region in space and time, I have to travel at a speed faster than the speed of light. This allows us to diagram causal structures in space and time. In particular, if I have a particular point in space and time, the causal future, everything that can be influenced in the future by that point in space and time, lies inside what's called the future light cone. The causal past of that point, everything that can have had any influence on it, lies inside what's called the past light cone. And everywhere else in space and time, what I've labeled elsewhere on this diagram, are places where you would have to travel faster than the speed of light in order to access. So this is the neat thing about these space-time diagrams is you can draw out this future region and past region of regions of space and time and understand how causality works. So only things in this past light cone can have a causal influence on this event in space and time, and only points in this future light cone can be causally influenced by it. Well, for example, in Einstein's special theory of relativity, the time has an infinite extent into the past. And so this past light cone in particular extends infinitely into the past. But in Big Bang cosmology and in what's called a Friedmann-Robertson-Walker space, the universe has a finite age. And so in this picture of the Big Bang now, if we draw it in space and time, we are here. This is our past light cone. So as we look out in space, we look back in time. Time is on the vertical and space is on the horizontal. So as we look out in space, we look back in time, but we can only look back in time a finite amount. In fact, the Big Bang in this picture takes this infinite space and chops it off at some finite time in the past. So here, once again, you see the Big Bang happening everywhere in an infinitely large space at once at some finite time in the past. And what it does is it chops off all the past time available in the universe and says nothing before this. And in fact, it's not hard to see that our observable universe, our horizon, is just the size of this past light cone as it intersects the surface of the Big Bang itself. Now, this is kind of a problem because when we look at very distant things like the cosmic microwave background, for example, so if we look out to when the universe was really young, for example, this light coming from the surface of last scattering when the universe first became transparent, we're looking out in space and back in time. So if we look in one direction, we'll see a point in space-time over here. If we look in another direction, the light will be coming from a point in space-time over here. But if we look at the past light cones of those points, the causal paths, those light cones don't overlap. What that means is that the size of the observable universe was so small at the time the CMB was emitted that one spot on the sky can't have communicated with another spot on the sky within the time available. The size of the observable universe when the cosmic microwave background was emitted was only about 380,000 light years. What that means is that if we look on the sky, the observable universe from the point of view of somebody sitting on the CMB was only looks like about 1 degree on the sky to us today, about twice the size of the full moon. And any 2 points separated by more than a degree are causally separated. They can't talk to each other at all in the entire history of the universe. So that means that we have a problem, right? How did these 2 points get to the same temperature with 1 part in 100,000? There's no mechanism for doing that in a standard Big Bang cosmology. You could assume it as an initial condition, just assume that the universe started out uniform and thermal equilibrium. But that's not an explanation, really. It's just an assumption. So we have this mystery now that the Big Bang doesn't explain how the universe got to be so uniform in the first place, because there's no way that these 2 points on the sky could have talked to each other in the history of the universe that was available to them. This brings us to what I work on, which is called inflation, which is defined to be, for all working purposes, a period of accelerated expansion preceding the hot Big Bang. So if there was a time really early in the universe where the expansion was speeding up very rapidly instead of slowing down, something new happens, which is that the observable universe during this inflationary period stays about the same size, but the space expands so rapidly that things that are initially inside each other's observable universe get stretched outside. And what this means is you can take a tiny little spot in the universe, exponentially stretch it out to be about the size of our universe today, and that can explain this high level of uniformity and equilibrium in the early universe. This, in 2 minutes, is the basic idea behind inflation. And on this space-time diagram, what it means is that instead of the Big Bang, the initial singularity of the universe happening at this point, it's actually not the Big Bang at all. It's the end of this inflationary epoch. So what you do in order to explain the uniformity of the universe is you put on this period of inflation that in a sense happens before the Big Bang itself. So question, single universe or multiverse, what's your opinion about it? It turns out that if you write down a model for inflation, and you can do this with particle physics theories and so on, which is something we won't get into, almost every model of inflation that you would write down tells you that the universe that this process of inflation is going to go on indefinitely in most places and only end and turn into a universe like ours in isolated places. But that will happen in isolated places an infinite number of times. So an almost inevitable prediction of this inflationary picture of the early universe is that our universe would be just one of an infinite number of universes, each one itself infinitely large, embedded in a larger inflating space. So you're going to have an infinity of infinities. And this is the idea of the inflationary multiverse. And it's an idea that I spent a lot of time resisting. I mean, I have to admit, I don't like it. But at the same time, having worked on it a lot, I've come to realize that there's almost no way around it. And it's just an inherent feature of this kind of cosmological model, is that you end up with this wildly profligate multiverse at the end of the day, where this universe is, does the inflation model suggest we can't see before that period? We can't, actually. So the thing here is that basically one of the properties of inflation is whatever initial conditions there were, whatever got inflation started, whatever happened before inflation got going, is completely erased. Inflation is this basically huge cosmic eraser that takes whatever initial conditions were there and stretches them out and dilutes them so much that they become impossible to observe. So all we see is the very end. All we can see in our observable universe. Remember, we can still only see this little finite bit. So all we can actually really see is the very end of this inflationary epoch. We don't have any access to the earlier parts of inflation, which are still, which would require us to see things that are outside of our current observable universe. And so we're stuck with this very limited amount of knowledge that is defined by the finite size of our observable universe. And we cannot, even in principle, access these other universes or the outside multiverse. So it's a weird, almost not a scientific idea anymore, because it's impossible to test. So this is one of the things that makes inflation as a theory very frustrating, is that it makes predictions that are in principle impossible to test. How can we connect the result of Schrödinger's cat with the existence of a multiverse? This is a different kind of multiverse. So you're thinking about the many worlds interpretation of quantum mechanics, in which, for example, anytime any quantum event happens, the universe splits into two. Sean Carroll just wrote a book about this recently. That is a completely different kind of multiverse than the inflationary multiverse, which is actually real physical spatial universes separated from each other in real space that exist independently. So this is something. This is a completely different sort of multiverse than the quantum one that I think you're thinking of. Are there any other questions about the physics? All right, let me just finish up by very briefly. Do I have about 5 or 6 minutes? Is that okay? Someone tell me if, yeah, it's good. All right. So when he invited me, asked me to also just talk about careers in physics and being a scientist and sort of what kind of advice I would give you folks as young people who are interested in going into careers in the sciences. And I think probably the best way to sum it up is to quote the guy who's one of my great science heroes, the physicist Richard Feynman, who said, study hard what interests you most in the most undisciplined, irreverent, and original manner possible. And I think that this is a great quote that sums up a fantastic attitude toward the idea. And so I want to dive into this a little bit more specifically. And one of the things is, so I have 4 general points of advice that are things that maybe you wouldn't hear from other people when you're thinking about going into a career in science. So what are the things that you need to learn and do? First one is learn to communicate. One thing that happens a lot is, or it has happened to me a lot, is I get high school students who say, you know, what should I, if I want to have a career in science, what should I study in high school in order to prepare me for that? And the answer that I give every time is theater or speech and debate. Science is about communication, right? You don't do it in isolation from other people. You do it in community with other people. And in order to do that effectively, you have to learn to communicate with each other. And so one of the things that scientists do is, like I'm doing now, is you have to get up in front of other people, you have to talk, you have to communicate ideas, you have to be able to respond to an audience. And so if you have a background in performance, in theater, speech and debate, this kind of thing, that is really excellent preparation for something that is an essential part of any kind of scientific career. And this is something that I think that a lot of, sort of geeky science people don't necessarily think of when they're in high school, is that you actually, science is a social activity. And so any kind of thing that you can be doing now that gets you used to being up in front of an audience and communicating with other people is going to be enormously beneficial to you going forward. So first piece of advice, take theater, performance of any kind. It's going to be really helpful to you. Second piece of advice, learn to code. There is almost no area of science today that does not involve some sort of computational analysis. It's ubiquitous. It's baked into everything at this point. And in order to be an effective scientist, it's not just pencil and paper and math. You have to be able to use a computer. One of the things, when I look at, for example, incoming graduate students to our physics program, one of the most common deficiencies is lack of knowledge of basic programming skills. In fact, a lot of undergraduate physics programs these days really don't teach or require computer programming. And I think that's a huge mistake. And so if you have good computer skills, if you learn how to code, if you know your way around a computer program, if you know how to do numerical analysis, know how to write video games, anything, that basic workman skill is going to be something that's going to put you head and shoulders above a lot of the other people around you, because it's still not something that is emphasized in a lot of science programs, and it's absolutely essential to doing research. So learn to communicate, learn to code. Number 3, don't be afraid to take a non-traditional path. Something that I see is one of the most common problems with students in graduate school that the graduate students have, people who are really trying to work on doing a specialized scientific career, is a lot of them just kind of sleepwalk into graduate school because it never occurred to them to do anything else, right? And what happens almost always is about 2-3 years into their graduate program, they find they're unhappy. They're not really enjoying their life because lots of science is actually a lot of drudgery. It's not always really exciting aha moments. Most of it is very boring. And they've never really thought about why they were there in the first place. And and there's this crisis of confidence that happens to a lot of people that about halfway through their graduate careers. One way to avoid that is to keep an open mind, and lots of students are also, when they come into graduate school, they're very focused. It's like, I want to be Stephen Hawking, I want to do string theory or quantum field theory or quantum gravity. And that's great. I mean, that kind of ambition is wonderful. But at the same time, there's all these opportunities that are available that maybe you're not looking at. And so instead of my advice would be, don't be too focused, but actually maybe meander around a little bit and keep an open mind for a while earlier in your career, because that means when you finally settle down later in your academic career, you're going to actually be really focused. I can give my case as an example. After I finished my undergrad, I was really burned out. I didn't want to go to graduate school. So I went out and I got a job in industry. I wrote computer programs for banks for 5 years. And by the time I finally decided I wanted to go back to graduate school and actually do a career in science, at that point I was really focused and I treated it like a professional obligation. And I was one of the few people I knew in graduate school who didn't have this crisis of anxiety about halfway through my graduate career. I really enjoyed graduate school because I knew that I could walk away from it at any point and I would be fine. And this is true of a lot. In fact, the job market in physics in particular is terrible, right? Any job you apply for has 200 applicants, is cutthroat competitive, and you'll be less afraid of that, and you'll be more able to be effective if you realize that there's all kinds of options for you, and there's all kinds of careers that somebody with a good science education can ultimately end up in, even if academia doesn't work out for you. And so taking a non-traditional path is a way to sort of soothe some of that anxiety and see the larger picture in your career and yourself. Finally, as a researcher, what makes you different is what makes you valuable. This is something that is exactly the opposite of most of the rest of your educational career, right? So when you're a young student, you're working hard on learning the basics, getting good grades in your classes, getting good exam scores, and these are all good things. But then when you actually start doing independent research, those are all things, being good in your classes, taking exams well, all of that kind of stuff. Those are things that make you the same as everybody else. Those are skills that everybody has to master, right? But on the other hand, when you start to do research, it's exactly the opposite. All of the ways in which you are like other people are the ways in which you are boring, and the world doesn't need your contribution so much. But it's the ways in which you're unique that actually make you valuable as a scientist. It's the ways that you think differently rather than the ways that you think the same. And that's hard, and this is a very hard transition to make because most people are taught to think the same in their educational backgrounds. Everybody takes the same tests, everybody takes the same classes. It rewards this kind of uniformity of thought that then becomes a liability when you actually have to become a practicing scientist, because it's your individuality, it's your uniqueness that is the most important thing. That's where your real original contributions to human knowledge are going to come from. Because once you start doing research science, you're out beyond the edge of what people already know. You have to invent it as you go along. And so always nurture your own individual viewpoints and your own individual talents. And this is one of the reasons why diversity in science is so important, is because lots of different viewpoints result in better progress than a complete uniformity of thought. So always keep that in mind. It's your differences, it's your uniqueness that is your strongest asset as a scientist and as an original thinker. And I'll end with that and say thank you very much for your patience. I think I ran a little long, but I hope it was worth it. And I'd be happy to entertain questions for as long as you guys like to stick around.
Okay, thank you very much, Dr. William, for such a great presentation. So we have a question from Jason Adams. So Jason Adams says, so Dr. Kinney, the universe does not have a midpoint. And also, what are your views on cyclic cosmology?
Okay, let's take the first question first. So the universe does not have a midpoint. Is that what the question was?
So does the universe have a midpoint?
No, that's the point. So there is no special place, right? This is the basic cosmological principle, is that every place on average, at least, is the same as every place else. So there is no midpoint. There is no point from which the expansion originates. It is like, I think of that uniform grid of squares, every point is the same as every other point, so that there is no midpoint to the universe. There's no center and no edge. This is the central idea behind all of the structure of the universe in cosmology. Second question, what do I think of cyclic universes? I've worked a lot on them. And the problem with cyclic universes is they don't work very well. The basic Big Bang cosmology has these problems where you can't understand the homogeneity and so on and so forth, and inflation solves some of those problems. One thing that inflation doesn't get rid of is the fact that the universe had a beginning. Even in these inflationary models, inflation had to come from somewhere. And there's a very famous theorem by author authors Borde, Guth, and Vilenkin that show that even in any inflationary cosmology, there still had to be an initial singularity. There had to be a beginning point. So inflation doesn't get rid of the need for a beginning of a universe, which makes physicists unhappy. People hate that, right? And so people have tried to come up with cyclic cosmologies that get rid of that. Unfortunately, in solving that one problem, they introduce so many other problems that it's very difficult to actually construct a useful and workable model of this. And so I've really become very pessimistic about the possibility of success for a cyclic universe. They really don't work. And it looks very much like the most reasonable conclusion you can take from the structure of the universe that we see today is that it really did have a beginning. And we might just have to live with that fact, even if we don't like it.
Okay. And the next question is, how far are we from making a gravitational telescope which can convert the gravitational input into an output that we can interpret?
That's a great question. And so we're in the process now of making gravitational wave telescopes like LIGO and Virgo, and I assume that's what the question is about. There are proposals to make space-based gravitational wave telescopes that would be much more sensitive and would be able to see different frequencies and so on. One of the things, remember I talked about this surface of last scattering, this point where the universe becomes opaque and cloudy, as far out as we can see in light. If we can use gravity waves, we can see further back than that. And we can actually, in principle, one of the things that inflation predicts is the generation of what's called primordial gravitational waves, is that inflation itself generates gravitational waves that may well be accessible to future generation telescopes, which means that with a gravity wave telescope, we could actually see all the way through that thick, cloudy soup of the early universe and actually see all the way back to that Big Bang. So we could really see back to the what used to be the initial singularity is now the end of inflation. In gravity waves, you could image all the way back to that, and you could actually, in principle, create an image of the Big Bang itself. So this is super exciting, and the answer is yes, people are working on it.
Okay, thank you very much. And the other question is there any relationship between the formation of Smbh and the Big Bang?
I assume by Smbh you mean supermassive black holes. And the answer is that's probably not directly related to the physics of the Big Bang itself. It's a phenomenon that happens later in structure formation and cosmology. So it's very closely related, for example, to the physics of dark matter. The mechanism for the formation of supermassive black holes is not completely understood. And this is still an area of active research, but they're probably not primordial in the sense that they were created in this very early universe. They're something that probably happened later. There are plenty of theories in which the dark matter itself is made up of primordial black holes, actually black holes that are created during this inflationary period. But these would be much smaller. Typically, they'd be less than an Earth mass or so. So these would be really, really light. The available window for primordial black holes as candidates for dark matter is somewhere around between like about 1/10 of the mass of the moon and about 100 times the mass of the moon. So really little ones. If most of the dark matter is made up of black holes, there'll be in little tiny ones, not in supermassive ones. So the supermassive black hole is more of an astrophysical phenomenon than an early universe one, if that answers the question.
Okay, and this is a general career advice question. So the question is, should I focus on Python as a programming language instead of other languages for computational things in cosmology?
Python's a good choice, in my opinion. It's very flexible. There's lots of libraries, especially with astrophysics and numerical analysis. It's easy to use, and so I think that I would say that Python is an excellent choice. It doesn't, at the end of the day, it almost doesn't matter. Once you learn the principles of programming, you can always pick up a new language pretty easily. Once you learn one, it gets a lot easier to learn another one. So it almost doesn't matter which language you pick, as long as you learn to use it. And so I would say Python's a great choice.
Okay, thank you very much, Dr. William. We have a question from Alan. So Alan is saying, do you think the future proposed collider at CERN is a good investment of time and money? And when LHS was proposed, people were so optimistic about finding out SU particles which haven't been found. So how likely does the proposed dark matter particles would give us the same result?
Yeah, it's an excellent question. It's a hard one to answer. I think that the consensus in the field is that people would like to see a successor built. But I mean, you're right in that there were lots of very confident predictions that we would be seeing new physics, new kinds of particles, in particular the SUSY theories. That's an acronym that stands for supersymmetric, which is an extension to the standard model in which every particle we know about, all the quarks and electrons and neutrinos, have a shadow partner, a supersymmetric partner. So that every particle in the standard model has a partner particle, and which is a prediction of these theories. And the expectation was that if these theories are correct, that we should have been seeing these super partners, these extra particles at the LHC, and they haven't arrived. That's science, right? Is that ultimately reality is the arbiter of things. It doesn't matter how beautiful your theory is. If it doesn't agree with the experiment, it's wrong. And it's looking worse and worse for supersymmetric theories. There's still regions of the parameter space that are compatible with data, but they're getting smaller. So the question is, I mean, you might frame the question in a couple of ways. One is it likely we will see new particles if we go to a 100 TeV collider instead of a 10 TeV collider? And the answer to that is, who knows, but maybe not. And I think that the argument here is that what people are thinking of trying to do is really carefully studying the Higgs boson itself. That one new particle that we found at LHC was the Higgs. We expected it to be there, but LHC was the first one to actually observe it. The hope is that by studying the Higgs very carefully, you might get some clues about what physics beyond the standard model is. You know the physics beyond the standard model is out there because there's dark matter, right? We only know what 4% of the universe is. The other 96% is completely invisible. So the hope is that you might find out some clues that would allow you to understand that other 96%. Whether it's a good investment relative to other things, there's a lot of debate in the community about that. I think the larger consensus is that it's probably worth spending the money, and I would tend to agree with that.
Okay. And the other question is, how do we actually calculate the exact percentage of dark matter, and when it doesn't even interact with light? And what about dark energy?
Right, so how do we know it's there in the first place? And the reason for that is because we see its effects indirectly. We see the gravity from the dark matter making things we can see move around in ways that we couldn't explain without it. So for example, galaxies rotate more quickly than we would expect from just the luminous matter in them. And that extra rotation means that there's an extra gravitational force that tells us there's some more stuff in there that we're not seeing. We also see it in galaxy clusters, in every structure in the universe we look at. When we look at the motions of the things that we can see and reconstruct what must be creating that gravitational force, we find that there needs to be more stuff in there to explain it. And so at every scale, all the way from the observable universe down to the scale of galaxies, we need this dark matter in order to explain the motions of things. So the answer for the dark matter question is we see it indirectly. Dark energy is more difficult because it doesn't clump. That means it has very little effect on the motion of things inside galaxies and so on. And the only way we detect dark energy is by looking at the expansion of the universe as a whole. And it's this discovery that expansion was accelerating that led to the need for dark energy. There are some other more subtle indirect effects, but the big one is this acceleration of the expansion of the universe as a whole allows us to infer the presence of dark energy. And there's just no way to explain it without a lot of dark energy there.
Thank you. I now hand over to Julia. Julia has some questions.
Hi, hello. Just wanted to thank you for an amazing lecture. And
Nice
I have two questions. So the first one is, what about Penrose's recent theory, the one involving Hawking points?
That I'm not so fond of. And I think that this is the Penrose cyclic universe that you're talking about. Am I correct?
I think so. It's from Aaron Odom.
Yeah, that's it. That's the one.
That's the one. Okay. Yeah, I think that one in particular really doesn't work like Penrose claims it does. I mean, all respect to Roger Penrose, he's a giant in the field, but I don't think this is one of his best ideas. And in particular, he's made a lot of claims about being able to see ring-like structures in the cosmic microwave background that would be relics from this earlier universe. Those really aren't there. And all of the the people who are really good at seeing the data are pretty much agree that those structures are not there as claimed. And so there's a lot of, there's no evidence for it at all, despite some claims in the literature. So, I'm very pessimistic about those particular models, actually.
Okay, and we have one last question, and then we can let you go.
Sure, no problem.
So this one is from Abhizek Kale, and it is, what parts of mathematics do you use in your research?
What parts of mathematics? I use primarily, so in order to do the kind of work that I do, which is you're talking about the very early universe, which means it's at the boundary between particle physics and astrophysics. So you have to be able to do both. So I do a lot of work with general relativity, and the primary mathematical field that is involved in general relativity is differential geometry. But I also do a lot of quantum field theory. In particular, I do quantum field theory and curve backgrounds, right? So that it's a combination of field theory and relativity. So you have differential geometry, you have linear algebra, you have a lot of quantum mechanics and a lot of quantum field theory. So my particular work meshes all of those together. So that the level of math that is required is pretty high. And so this is something where in this particular field, you really can't be productive in research until after you've finished most of your graduate classes and then studied some more stuff for another year or two. And then you really have the mathematical background to start doing really serious work. So there's a long learning curve to it.
So that's it. The questions are done. So I'll pass now to McDonald.
Okay.
Okay.
Thank you very much, Dr. William. This was a really great presentation, and I think everyone really agrees with me. And to everyone, thank you very much for joining the Connecting the Young World Fair from different parts of the world. We really appreciate it. And stay tuned. We have another lecture at 3:10 GMT. So see you there at our next lecture. Thank you, everyone.
Yeah, it's Robert Brandenberger, right? He's super cool. He's a great guy. Yeah, you'll like that. Okay, wonderful talking to you all, and I hope you have a great rest of your day. Thanks for listening.
Okay, bye, everyone.
Bye-bye.